MBA633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this segment, we will work a problem in which we will develop the confidence interval for the difference between two population means when the population standard deviation is known. It's exactly the same problem that we used to work a hypothesis testing problem for a similar scenario. So the problem setting is the following. As part of environmental protection, an agency monitors the alkalinity level of a river at various points. The two populations that are of interest here, one is the upper reaches of the river and the second population is the lower reaches of the river. The narrative tells us that the two population standard deviations are known. So we are told that the alkalinity level at the upper part of the river is normally distributed with a standard deviation of 10 milligrams per liter, and the alkalinity level at the lower reaches of the river is also normally distributed but with a standard deviation of 25 milligrams per liter. So the sigma 1 and sigma 2 are given to us. Now we want to construct a 99% confidence interval for mu L minus mu U, the average alkalinity level in the lower part of the river and the upper part of the river. What's the difference between the two? And one could think of reasons why we want to do that. Perhaps the upper part of the river is very pristine and there is more industry in the lower part of the river, and you want to test if there is any significant level of pollution and so forth. So that might be the practical setting within which this kind of a problem might be solved. So to compute the confidence interval, we take two samples. So for the lower reaches of the river, we sample water in 15 different places. The sample size is 15. For each of those 15 samples, we compute the alkalinity and we get a sample average of 99 milligrams per liter for the lower part of the river. And then for the upper part of the river, we take 10 samples of water and average the alkalinity levels of those 10 readings and get 80.5 milligrams per liter. That's the sample mean for the upper part of the river. So since we want to compute a confidence interval for the difference in the two population means, the sample statistic that I use is x bar L minus x bar U, the difference in the two sample means, which ends up being 18.5 milligrams per liter. So that's the sample statistic. That's the basis of our confidence interval calculation. So you remember how confidence intervals are calculated. We take the sample statistic and we surround it on two sides by a margin of error. Okay, so that gives us a lower limit and an upper limit. The lower limit is simply the sample statistic minus the margin of error. The upper limit is the sample statistic plus the margin of error. So our next step would be to determine what is the margin of error, and the basis for that is how confident I want to be. I want to be 99% sure that the range, the confidence interval that I have, will include the unknown parameter difference that I'm trying to compute. So in terms of our distribution, you know that since the standard deviations of the two populations are given to us, 10 milligrams per liter and 25 milligrams per liter, since the two sigmas are known, the sample statistic being used here, x bar L minus x bar U, is normally distributed. Okay, and the standard deviation of the sample statistic, in other words sigma of x bar L minus x bar U, is given by this expression. You have seen exactly the same expression when we did the hypothesis testing case for this problem. If you plug in the numbers that are given to us in the narrative, 25 milligrams per liter for the lower reaches, 10 milligrams per liter for the upper reaches, and you plug these numbers in, you get a value of 7.19 milligrams per liter. That is the standard deviation of the sample statistic, which is x bar L minus x bar U. So we will keep this number handy. The next step is to compute a margin of error in standard deviations. So this yellow shaded area that we have here has to be 99%, because that is the portion between the upper limit and the lower limit. You can see the way we have drawn the upper and lower limit. The upper limit is the sample statistic plus the margin of error. The lower limit is the sample statistic minus the margin of error. So what should U be? That's essentially what we're trying to find. And you know that we have to use the norm S inverse built-in function to do that. So let's try. and do this, equal to norm S inverse, and the value I put in is not 99% but 0.995, because norm S inverse needs the area completely to the left of you, not just the yellow shaded portion in the middle. So this ends up being 2.575. So this 2.575 is the margin of error, but in standard deviations. So my margin of error has to be 2.575 standard deviations large. So in milligrams per liter, how much should the margin of error be? I think you can guess where we are headed with this. So the margin of error in milligrams per liter is the 2.575 standard deviations. That's how large it has to be in standard deviations. And how much is one standard deviation? It's simply 7.19 milligrams per liter. That is what we computed over here. Okay, so this is in milligrams per liter. All right, so what is the end result of this calculation? I am 99% sure that mu L minus mu U, the difference in the average alkalinity in the lower and upper reaches of the river, lies between 18.5 milligrams per liter plus or minus 18.51. Okay, so approximately, do you notice this range is between 0 and 37 milligrams per liter. So this is dangerously close to 0. Now, if this interval had included 0, suppose this lower limit had been -1. So if we ended up concluding that I'm 99% sure that mu L minus mu U lies between -1 and plus 37, notice that it would have included 0 in that range. Then you cannot be statistically sure that there is any difference in the average alkalinity between those two populations. That is how confidence intervals and hypothesis testing are actually related. But for our purposes here in this problem, let me just draw a line over here, just so we can read properly. The end result of this calculation is I'm 99% sure that mu L minus mu U, the difference in the average alkalinity level in the lower part of the river and the upper part of the river, lies between 0 and 37 milligrams per liter.